Good morning and welcome to our STEM podcast. I'm here with Chuck White. My name is Rich Kingsford, and we're from ChemVantage, chemvantage.org, which offers affordable, high-quality LTI homework, quizzes, and assignments for general chemistry. The topic today is how to scaffold problem solving for students who freeze. I love this topic. I love the word scaffolding. Our first question, what does the phenomenon of problem-solving freeze look like in a STEM student, and how is it different from simply being unable to solve a problem?
Well, Rich, I think any kind of freeze in STEM courses really stems from cognitive overload. And so if you see a student, staring at a piece of paper without moving, that's usually a sign of freezing. Sometimes it could be, suddenly shifting to other things like busy work or phone or something like that, but really not focusing on the problem. The difference between a student who freezes and somebody who's unable to solve a problem is that the person who's unable to solve a problem will usually just go ahead and start it. And maybe they'll make a mistake somewhere through the process. But a student who freezes probably won't even start the problem because they're just overloaded at the very beginning.
Yeah, completely agree. I'm thinking there's a that freeze look is a lack of confidence, and we all know what that feels like, where you're looking at something and say, "Oh, what am I going to do here?" Just very little confidence going into the problem.
Or a deep belief that they're just incapable of doing it.
Yeah, agreed. Moving on, how does the mindset of learned helplessness contribute to a student's tendency to shut down when facing an unfamiliar problem?
I like this term, learned helplessness. Um, it's basically turning a statement like, I don't know how to do this problem, into another statement like, I'm not a math or science person, and nothing that I do will change that. It is really um, a, a, a focus, a change from the microscopic, this problem, to the macroscopic, I'm not a STEM person or I'm not a chemistry person. And so, how does that contribute to a student's tendency to shut down? Um, when students experience unsupported failures, repeated unsupported failures, they attribute that failure to stable internal traits, like I'm just bad at chemistry, rather than a lack of effort or strategy. So when they're faced with an unfamiliar problem, their brain tells them, attempting this will only lead to pain and will confirm my inadequacy. So the safest thing is to just not try it. So it turns into a defense mechanism where students shut down rather than think that they're going to confirm any fundamental inadequacy in themselves as a person. When really, it's just a matter of having not been supported well enough to develop skills to solve a problem.
Yeah. Yeah, I mean, I'm thinking I'm not a that phrase, I'm not a math person, I'm not a science person. I think that I completely agree. There's it's easy to think that, but it's it's such it's a logical fallacy, right? I mean, no one is born a chemistry person, no one's born a math person. It's there's a quote I'm thinking of. I maybe it was Albert Einstein that you the best learning you do at college is you learn how to think. I think a lot of us are on the step one of 100 on learning how to think. But I think as you struggle, as you grind through, as you slowly build confidence on these problems, you're learning how to think, you're learning how to reason. And that's a beautiful thing. I value that struggle and that pain and suffering and maybe even that lack of confidence, so long as you start, so long as you say, okay, I'm going to take that leap of faith and and take identify step one and start walking.
Yeah, I'm not sure that the pain is really necessary. If you can show students the way, then they can succeed through practice. And practice is absolutely necessary to develop those skills. A little bit of pain probably comes along with it along the way.
Yeah, I like that, but minimizing it if at all possible.
Yeah,
I like that. Maybe that's one of the roles of a good teacher.
I hope so.
Moving on, I thought this question was kind of rephrasing, but we'll do it anyway. How can we distinguish between a student who freezes because they lack the basic skills and one who freezes because they're overwhelmed by the problem's complexity or length?
Um, well, so if you if a student freezes because they're overwhelmed, then they've just shut down because of cognitive overload. But if they if they lack the um, if they lack the basic skills, they won't be able to do the problem. If they've frozen, but they still have the skills, then you may be able to reveal that by really isolating on a smaller part of the problem. So many of the difficult problems, at least in general chemistry, involve multi-step problems. And if you can just isolate on a single step, either at the beginning or possibly even at the end of a problem, then you can ask a simple question. You know, if you need an answer in grams and you somehow magically had a value in moles, could you convert from moles to grams? And the student may say, well, yeah, sure, you have to multiply by the molar mass. And that's correct. And so a student can do a single step of the problem. And then all you have to do is show them that if they take multiple steps and do them one at a time, then they can get unfrozen and do the problem. But if a student doesn't have the basic skills of how to manipulate units or how to isolate a variable in a simple algebraic equation, well, then that requires a lot more remediation.
Yeah, I like that. I'm thinking identifying that those steps is a challenge in and of itself. It's very possible I, as a student, could read a question, and even if there's one word in there, one key word that I don't that I'm misunderstanding, maybe I think it's something else, or I have no idea what it means. I'm gonna struggle. I might freeze. I'm gonna struggle with, okay, I don't understand this question. How am I going to step through it if I'm too unfamiliar with those basics, that so unfamiliar that I can't even understand the question?
And that goes back to a fundamental problem, and that is that many students, don't read very much anymore. And so they don't have the reading skills or the vocabulary skills to get the context of a question. So that's a real problem.
Yeah. I think once you've identified it, I think the solution's pretty obvious. We step back and work on those basic skills. I think it's that identifying it, seeing it, that's the first step. And I think that's even it's a first step in problem solving too, is breaking it down into those small steps, something manageable.
Yep.
Moving on, what are the key components of effective problem solving, scaffolding, that need be taught explicitly taught to struggling students before they begin?
I think first thing is for students to be able to read a story problem and to try to figure out at a very high level what's going on in the problem. What are you starting with? What is the goal of the problem? Uh, you'd be amazed at how frequently students lose track of what they're doing because they don't have the correct orientation of what's going on in the problem. A second thing would be figuring out a pathway, mapping a path from the things that they are given or things that they know to the goal of the problem, what the answer should look like. And then finally, once they have the pathway, then there's the actual execution of calculating the numbers and checking the answer to make sure that it makes physical sense. So it, I always have encouraged students when they get a final answer or even an intermediate value to ask themselves, does this value make sense? Does this value pass the smell test? Because if they're calculating something and they get an answer of 10 to the 50th grams or something like that, well, that's like the mass of the solar system or the universe or something. And so it doesn't make any physical sense. So you have to really keep track of not only running the calculation, but also figuring out whether the answer makes any sense at all.
Yeah, I love that. Maybe that's a fourth test is the testing phase.
Yep.
What I love all four of those: orientation, mapping, execution, and then testing. That's the cool thing about any STEM subject is it's logical, and anything logical can be tested. And you can ask yourself, does this make sense? Does this sound right?
Yeah, and testing doesn't have to wait until the end. The intermediate values that you calculate in a problem can also be tested for reasonableness.
Yeah, very good point. Moving on, how can we use a Think-Aloud protocol in class to make the complex process of expert problem solving visible and achievable for students who freeze?
This is a really good point because um, when we, as teachers, as experts, solve problems, we don't always verbalize what we're thinking about. And so when we work a problem, it looks like magic to a novice. And so verbalizing, thinking aloud as you solve a problem is a really good strategy. When I work problems on the board, or when I did before I retired, uh, I would often do it with a problem that I had not prepared for. And so I didn't necessarily have notes or memorized the pathway. And I didn't have a calculator with me, so I did back of the envelope math. And so I would start a problem and then just verbalize my way through figuring out what the pathway was from the knowns to the goal of the problem. And then I would write on the board the math, which involved, just approximate numbers, 2 digits, um, and lots of rounding. So when I got to the end, I could say, well, I didn't have a calculator, but the answer should be sort of like this within a factor of two or so. Um, uh, so, it might go something like, um, okay, I see three different numbers here to start with. Honestly, I'm not sure which equation to use first, but let me write down what they represent and see if a pattern pops out. And, wait, that unit doesn't match. I've got something in grams and I've got something else in kilograms. Let me stop and fix that. I'll convert the grams to kilograms so that I can work these things together before I go any further. So um, show the students that being stuck is a normal part of the expert process and not a sign of failure. So they can um, emulate, you should emulate what you want them to do when they're solving problems. Students are oftentimes just amazed by back of the envelope math. They ask me, how in the world did you do that? And with 2 digits, you can do multiplication and division in your head just as in an approximate way, um, and get reasonably close to a final answer. So showing them just cold how you would go through a problem makes it look much less like magic and much more like they can do it.
Yeah, and that's not easy. Showing that vulnerability and showing those. hey, I make mistakes too, or I get stuck too.
Absolutely, yeah, and you've got to find them and correct them, but making mistakes is an important part of the process.
I love that. Yeah, these are a lot of good points. That think aloud protocol. That's a great term. Moving on, what specific techniques can a teacher use to teach students how to break down a multi-step problem into manageable chunks to prevent overwhelm?
I use a graph to do this. And what I tell students is that when they were in high school, they were often asked to calculate some quantity B from another quantity A. And it was a one-step process. They applied some equation to A and they got B. And as long as they could figure out which equation to use, then that would solve the problem. But in real problems, in college and in research, you have multi-step problems where the quantity that you're after as a goal of the problem is not achievable in a single step from things that you know at the beginning. So you have to break it down into steps. And to form the pathway between the things that you know and the things that and the goal that you want for the problem really involves figuring out where all of those intermediate steps are. Now, in freshman chemistry, the intermediate steps often are just one or two places. So you can isolate a single step either at the beginning of the problem or at the end of the problem. I encourage students to work problems backwards. So start with the goal. Let's say the goal is a number of grams and of a substance. And you could ask a question, what would I need to know in order to calculate this final answer, grams of sodium chloride? Well, if I had moles of sodium chloride, then I could convert moles into grams by multiplying by the molar mass. Or if I knew the density of something, then I could get grams um, from the density multiplied by the volume. And then you'd take a look at the sort of things that you're likely to know and backward identify an intermediate step. And if you can do that process over and over again until you get to some information that you have access to at the beginning of the problem, then you can define the pathway from the end all the way back to the beginning. If that doesn't work, if you get stuck, then you can start at the beginning and you can ask, well, what things could I calculate from this starting point with the information that I have at hand? And so if your starting point is, something like the mass percentage of a material in a solution, then you could calculate the number of grams in a solution or something like that. And so you can go backward from the end or you can go forward from the beginning, and hopefully somewhere in the middle you could find a common intermediate place, and then you have a pathway, you have a connection all the way from the beginning to the end. And so um, doing this pathway really is the way to break down a multi-step problem into manageable single chunks, and that can help to prevent overwhelming the student.
I love that. Those two tools, approaching the problem backwards with the end in mind, and then moving forwards, starting from the beginning. Sounds like deductive logic and inference logic, inference reasoning. I don't know what the different terms are, but I'm thinking we do this all the time. It's just with the easier questions, with the easier problems that we handle every day, we do this same exact process. It's just so intuitive. And I'm wondering with struggling students, that might be a confidence builder to help them see how they do this very frequently. Just with they do it so fast that they don't realize it with very simple problems. And maybe showing them you're already using these tools could be a confidence booster.
Yeah, one of the examples I use is if you and four friends go out for pizza and you order pizza and drinks, and then you just split the tab evenly, you're going to have to take the cost of the pizza and the drinks, add them all up together. You're going to have to multiply by something like 1.06 to get the tax. You're going to have to multiply again by 1.2 to get the tip, and then you're going to have to divide by 5 in order to get the amount that each friend is going to have to put into the pot in order to cover the tab. So, and often all 5 people have to do that separately. You don't do the calculation together. And so, yeah, that's a 4 or 5 step process that you need to do in order to just estimate how much you need to put into the pot in order to cover the tab for a shared pizza.
I love that. You mentioned charts, and I wanted to emphasize that point. I love how charts can help me visualize these steps and the relatable story you just shared too. It helps me visualize the variables. I think that's, we when we draw on the board, we use X, Y, Z. We use one letter variables. And when I studied statistics, that drove me nuts. We wouldn't just use X, Y, and Z. We would use Greek variables. And I was like,
Mhm.
why are we taking something hard and making it even harder? When I learned programming, I loved how descriptive the variables were. In programming, you don't say X, Y, and Z. You would write out the variable name. And it's so much more intuitive. It's so much less cognitive work to solve the problem. You're making the problem easier to solve by helping you visualize, painting a vivid picture in your mind about what's going on. And usually there's a blank spot there, or there's a couple blanks that you don't know yet. But if you can make that imagery very vivid in the student's mind, I believe you can make a something that seems difficult much, much easier.
Yeah, it has to do with history and the way that notation developed in chemistry. One of the reasons they use Greek letters is because there are only 26 letters of our normal alphabet, and K, for example, is way overused. K is used for rate constants. It's used for Boltzmann's constant. It's used for equilibrium constants. It's used for a lot of different things, and it leads to some confusion and ambiguity. And so they branched out into alphas and betas and phis and so forth.
I sometimes I think we should teach kindergartners Python. Python is a very easy, simple programming language. And I'm just imagining these kindergartners solving these complex word problems using their programming skills. What would the world be like? Well, we're out of time, but hey, Chuck, thanks a lot. This is one of my favorite topics, and I appreciate your time.
I enjoyed it. Thank you.
Just a reminder, Chuck and I are from chemvantage.org, and that's a service that offers affordable, high quality homework that can be used on learning platforms like Canvas, anything LTI compatible. There are quizzes, there are assignments for general chemistry. Thanks for listening. Have a good day.